Okay, so we talk about Prim's algorithm to finding the minimum spanning tree. So this is a greedy approach. So let us talk about hallmark for greedy approach. Hallmark for greedy algorithm. Okay, so it is telling us greedy choice property. Okay, so a locally optimal choice is globally optimal. Okay, so this is the hallmark for greedy. So it is telling us a locally optimal choice, greedy choice basically is globally optimal. Okay, so we'll just talk about. So Prim's algorithm is a greedy algorithm. So Prim's algorithm is based on this theorem, which is basically a greedy choice, or which is basically coming from this hallmark. So this theorem is telling let T be a MST of a graph G, which is basically V comma E, and A is a subset of V, any subset of V, and suppose UV belongs to E is the least weight edge connecting V, sorry, A and A complement, V minus A. Then this theorem is telling this UV must be in the minimum spanning tree. Okay, this theorem is telling this UV must be in the minimum spanning tree. So what is the meaning of this? Suppose we have A set, we have some vertices, and this is the V minus A or A complement, this is the V minus A. Now, so there are some bridge edge. Bridge edge means one vertex, the edge which is having one vertex in A and another vertex in A complement. So these are we can call as bridge edge. So among these bridge edge, suppose this is the edge UV which is minimum among all these bridge edge. Okay. Then this theorem is telling this UV must be in the minimum spanning tree, and we have to prove this theorem, but before that let us understand this theorem. So this is telling us this UV, the bridge edge which is the minimum among all the bridge edges, and this H must be in the minimum spanning tree. Okay, so let us take the earlier example which we have, and we see we will prove this theorem, but before that, and the Prim's algorithm is based on this theorem. So let us just draw the graph we have in the last class we discussed. So suppose this is our graph. Okay, suppose this is our graph and these are the weight. So 5, 12, 14, 8, 3, 10, 7, 15, sorry 7, yeah 9, 15, and we have seen these are the, this is our minimum spanning tree. So this one, then we have this one, Okay. Now, we take some vertices A vertex, like we can take this vertex as A. Suppose this is our A vertex, and the remaining is V minus A or A complement. Now, we consider all the bridge edge. So, this is a bridge edge. The bridge edge means one edge, one vertex, so one part is in A, another part is in A complement. So, this is bridge edge, this is bridge edge, this is bridge edge. Okay. So, among these the theorem is telling the minimum. So, this is the minimum 5. So, 5 is in minimum spanning tree. Okay. So, if we take another A like this, say if we take this is as our A, suppose this is our A. Now, what are the bridge edge for this? If this is our A complement is all this. This is our A complement or V minus A. So, then this is a bridge edge, this is a bridge edge, this is a bridge edge, this is a bridge edge. Okay. Among these, which is minimum? 7 is the minimum, and we can easily check 7 is in the minimum spanning tree. So, that is the theorem is telling. So, this theorem is telling if we take any set A is a subset of the vertex. So, if we take this as A and if we take this as A say and the remaining are in A complement, then we consider the bridge edge, this 2 is the bridge edge. So, among this is the minimum. So, this has to be in the minimum spanning tree, and that is the greedy choice, and that is the locally optimal. So, that is the greedy hallmark. Locally optimal, a locally optimal solution is giving us the globally optimal. So, if you start with this vertex, we just take this minimum edge. Okay. So, this is the greedy choice. So, that is the locally optimal choice, and this is happen to be a globally optimal. So, that is the hallmark for greedy. Okay, let us try to prove this theorem. Then we will use this theorem to have an algorithm which is called Prim's algorithm. So, this theorem is telling us if we take a set A, any set A, okay. Suppose, so we take set A, so suppose these are the vertices and let us just draw okay. So, suppose we draw some vertices we are in A complement. So, these are in A complement and this one, say this one. Okay. Suppose these are in A complement V minus A and the white vertices these are in A say. Okay. And suppose, so we have say other, suppose this is the bridge edge, this is U and V. So, this is the bridge edge which is minimum weight, and suppose that is not in the minimum spanning tree. Let UV is not in the minimum spanning tree. So, we are not having this edge in the minimum spanning tree. Then we have to reach to a contradiction. So, that is the way method of contradiction we will prove this theorem. Okay. Now, suppose this is not in the minimum spanning tree, which is basically UV. So, this is the weight of, and the weight of UV is minimum. So, if this is not in the minimum spanning tree and this is a spanning tree, so basically we have a edge which is a bridge edge also, and that is the edge which is connecting from because we have to cover all the vertices. So, we have to cover A and A complement all the vertices. So, there has to be a edge where that edge is a bridge edge, and that is we are assuming that is not this one. So, suppose this is this one. So, instead of this, if you take this edge and if you remove this edge, then this is also a spanning tree, and this is the weight is minimum, because this is the minimum bridge edge. So, that contradicts the fact that that weight is minimum. So, it is a contradiction. So, minimum in the minimum spanning tree, this has to be, so this has to be there. Okay. So, this is the way contradiction way we prove this. Okay. So, now this based on this theorem, we have a algorithm which is called Prim's algorithm, which is basically greedy algorithm to find the minimum spanning tree. So, let us write the Prim's algorithm. Prim's algorithm. So, what are the input? Input is a graph, it is a undirected graph. So, and we have a weight on the edges, this is the input, and the output will be a minimum spanning tree. So, that is the output. So, what is the idea? So, idea is to maintain a priority queue. So, we maintain V minus A as a priority queue, Q, and we key each vertex in Q with the weight of the least weight edge connecting it to a vertex in A. To a vertex in A. Okay. So, connecting it to a vertex in A. So, basically what we do? We basically, so we have a graph. So, we basically start with a vertex S, and we consider, so now we start with a vertex. So, A is content initially S now. So, that is the starting vertex, it could be any vertices. Now, we consider all the bridge edge which is connecting from S to A complement basically. So, now and that is the key value of the vertices, and we put everything into the Q. Okay. And the Q is basically maintaining the, this is the priority queue, we are, it could be array also, it depending on how we are implementing. So, we can just have a array. So, if V is the vertex, so we can have a array if there are n vertices. So, V1, V2, V3, Vn. So, among these vertex we consider a vertex k Vk as S, this is our S. Okay. Now, we consider the we keyed this we keyed the weight of the each vertex as the minimum at the weight which is connecting from that vertex to A, and now we choose the minimum weight edge, and that is that must be in this minimum spanning tree, and that is the greedy choice. So, we capture that vertex in A, and slowly we grow the tree. So, we start with vertex S and slowly we grow the tree. So, that is the idea. Okay. Let us write the code, then it will be more clear. So, let us write the code for Prim's algorithm, pseudocode. Okay. So, initially everything is in Q. So, this Q is a priority queue, we can just have a array or the heap implementation for that, we will come to that. and the key value of V is infinity for all V in V, and except some vertex which is the starting vertex, which we put the key value as 0 for some arbitrary S from V. So, we choose a vertex to start, that is the starting vertex. Okay, then, so while Q is not empty, so obviously Q is not empty initially. So, we just extract the minimum from this Q, extract mean from this Q, and then after extracting mean, so then we just update this key value of the vertex which are adjacent to U, which are adjacent to this U. For each V in the adjacency list of this U, so what we do if degree of V, not degree, here we are using the key value, do if V is in Q and the U V is less than key of V, then we change, then the key of V is basically U V, W U V. Okay. And we make it a responsible vector. Now, U is responsible for the degree of V change. So, this is sort of responsibility vector. So, this is 6, 7, 8, 9, and finally, in 10 at the end this V comma pi V will give us the MST. Okay, so this is the code, and this operation is basically, this operation is called decrease key. So, if this key value is less, we are going to that particular position and we are making the value, changing the value. So, this is the decrease key operation. Okay, so, so this is the pseudocode for Prim's algorithm. So, basically what we are doing, we are starting with a vertex and we are initially we are putting every vertex to the key value is infinity, because initially nothing has explored except a vertex S. Okay. So, if we just implement this using a array, so we have a vertex, this is the array implementation. Suppose we have n vertices and we choose a vertex S, any of this vertex will be S, and initialization is, we are, this is the key value, we are putting everything is infinity except this has 0. Now, once we extract the minimum, so since this is 0, so this will be extracted, and this we are going to put in, basically extract mean means it is deleted from the Q and it is added in A. Okay. So, it is deleted from the Q, it is added in A. So, basically, so everything is infinity, 0 is the minimum. So, S will be the first U. Now, we consider S is any, we choose a arbitrary vertex as S, starting vertex. Now, we consider all the adjacency vertex of S. So, this is our U, is the first vertex. So, now it was having the key value is infinity initially. Now, this has a weight. Now, if the key value is less than, if the weight is less than the key value. So, initially it is infinity. So, obviously that if that weight is not infinity, so this will be less than. So, we have to change this key value. So, if this is say this vertex V, then it is infinity. Now, it has a, now this has some value. So, this value we are going to put over here. So, this way we update all the adjacency vertex of U. Okay. And we make a responsibility vector, like for this change, for this degree change, this vertex is the responsible. And then then we will repeat this until the queue is empty, then we will choose the next vertex. So, basically we start with a vertex and slowly we grow the tree, that is the idea. Okay, let us take an example how we execute this. So, this can be implemented using the heap also. In that case, the decrease key. So, we will come to the time complexity of this when we analyze the Prim's algorithm. So, let us take a quick example of the Prim's algorithm, how it is working. Okay, so suppose we have this graph, the same graph, let us draw. Okay, and these are the weight we have 5, 14, 8, 3, 10, 7, 9, 15. Okay. Now, suppose, so this is the input, this is the graph, we want to execute the Prim's algorithm. So, we put everything into the priority queue, it could be array, simple array. Now, so we put every key value, key of v is to be infinity except some starting vertex. Suppose this is the starting vertex. So, this is a S starting vertex and we put everything to be infinity, the key value, because nothing has explored. This is the initialization. Okay. So, now everything is in queue with the key value infinity except this vertex. Now, we extract the minimum. So, extracting minimum means, so now Q is basically all the vertices. Now, extracting minimum means it is getting the minimum, it is deleting from the Q and it is adding in A. So, this vertex is added in A. So, now U is basically S. Okay. So, now we consider all the vertices adjacent to this. So, these are the vertex. So, this is V. For this V key value was infinity. Now, this is 15. So, 15 is better than infinity. So, we have to decrease this key. So, this is now will be 15 and we have to put a mark that this is the responsible, this vertex is responsible for this change. So, similarly, this will be 7 and this vertex is responsible for this change. So, this mark is needed. So, let us use another color for this mark. Okay. So, this is now 10 and this vertex is responsible for this change. Okay. So, now this is our, now this is in A and this is in Q, V minus A. Okay. Now, again we will do the, so Q is not empty. Now, again we will do the extract min. If we do the extract min, who is the minimum? Everything is infinity except this. This is 10, this is 15, this is 7. So, this is our next U. So, we choose this U and this will be extracted from the Q. So, this is our next U. Now, if this is U, now we consider all the vertices adjacent to U. So, now this is infinity. So, this will be now 9 and we put a arrow there because for this change this vertex is responsible. Okay. Now, this is another vertex, this is infinity, now this is 12 and we have to put a arrow for this and also this is infinity, now this is 5 and we have to put a arrow for this and this is already in Q. So, we do not need to do anything. Okay. So, now we have to, now this is in, so we started with this, we captured this vertex. Now, who is the minimum? Now, 5 is the minimum. So, we extract 5 from the Q and put it in A. So, once we extract 5, so we check all the vertices which are adjacent to 5. So, this is vertex, this was infinity, now it is 14. So, 14 is better than infinity. So, we need to perform the decrease key operation. So, this will be 14 now and this is the responsible vector and now this one was 12. Now we have a better one which is 6, and now this was responsible for this change. Now for this change, so this has to be deleted. Now who is responsible? Now this is the responsible for this. Okay, that's why this sign is important. So this responsibility vector, who is the responsible for final change, and that will give us the minimum spanning tree. Okay, so now this is okay. Now this one is 10. Now this will be now 10. This will be now 8. 8 is better than 10. Now this was earlier responsible. Now this is now responsible. Okay. So now this is the situation. Now who is the next minimum? Next minimum is basically 6. So for 6 we have these two vertices, adjacency vertices, which are already in A. So we don't need to do anything. Which is the next minimum? Next minimum is 8. So this is our U. Now this V is already there. We don't need to do anything. Now we have to change this because this is 14. Now we have a better one. So 3, and this was responsible for this. Now this is responsible for this change. Okay. So now this is done. Now next minimum is 3, and but this, for this we have added everything. Now next minimum is 9, next minimum is this, and finally after this we will follow this link to have the minimum spanning tree. Okay. So this will give us the minimum spanning tree. So basically the idea is we start with a vertex S and slowly we will grow the tree. So we start with a vertex S and we slowly capture all the vertices in a greedy way. So that is the locally optimal choice, and it will become a globally optimal. That is the greedy hallmark. So we start with the vertex S, then we capture this vertex in a greedy way. So slowly we capture all the vertices. Okay. So this is the example of Prim's algorithm. So in the next class we will discuss we will analyze the Prim's algorithm and the time complexity basically. So okay, so we will discuss the time complexity in the next class. Thank you.